So I'm Ryan. I'm part of the collisions team at Quantemol, which means I spend most of my time working on QEZ. But I'm actually going to present today about a little bit of R&D that we've been doing about neutral dissociation and how we can sort of get better, clearer data, or at least start developing insights into what is actually going on. So this little cartoon I have for the general process of neutral dissociation. So we have a molecule. This one will come up later, so the details of it are not so important right now. But it collides with an incoming electron. It is excited from its ground state up into, in this case, the lowest triplet state. And then given some time, some dissociation happens, some bonds break, and we end up with two neutral fragments. So I just want to set the little sort of plant seed right now that this is very conceptually similar to photo-induced dissociation. If I was going to make the similar cartoon of photo-induced, I would basically replace this little cartoon electron with a photon. Easy work. So I also like to, thank you. Start all my neutral dissociation talks with this quote, which I've got quite a bit of mileage out of. So this paper was published a few years ago, where a bunch of big-ish names came to, together in plasma to talk about the state of plasma, sort of the big milestones of the past couple of years, but also the big milestones that are coming up in the future, challenges they're facing. And this quote sort of justifies this project in saying neutral dissociation, understudied, very important. And so I thought I would begin with saying, what is it that we actually do at Quantemol? So if somebody comes to us for a consultancy, and they say, we're interested in this molecule, which for now, we're all going to pretend that everybody's incredibly interested in methane. We would like to know about methane. We would like to receive a neutral dissociation cross-section. What is it that we at Quantemol would do right now? So first of all, we would use QEC to generate the excited, electronic excited cross-sections, which are here on the right. QEC found 6 excited states. You have your cross-sections up to 15 eV. We would then go just to MolPro and use this data to calculate the potential energy curves for all 6 of these states, which are here on the left. And then the key step that we would do is an assumption that this abstraction of just the hydrogen atom would be the most important neutral dissociation channel. Then we can take these potential energy curves. Oh, I'm pressing the wrong button. This one's my fault. We would take these potential energy curves and sum over all of the NN ranges where they are not bounded states. So where there isn't a significant well in the energy curve of the excited state, we essentially sum up the excited cross-section to get this here on the right. And because we have a lot of potential energy curves here that are not dissociative at all energy ranges, there is no sort of significant classic undergraduate chemistry professor skater stuck in a well type states. The difference between adding all of the states together and then having this little exclusion principle is not so different, but with more complicated molecules, you sometimes see that there will be quite a few jumps. So this is one of the more approximate methods of Quantemol, but approximate always doesn't just mean bad, but there are definitely some sort of idealized scenarios that you can very quickly imagine where this assumption is perhaps a little bit stretched. So here I have 2 molecules, both of which are very common in plasma. We have C4F8, and we actually have some QDB global model data on this molecule for neutral dissociation. So first of all, you cleave it in half and you get 2CF4. But then we also have that this fragment goes on to another process to generate either 2CF2 or CF3 and CF, which then brings in the question of how are we going to weight these? We have our excited cross-sections we can sum, but which goes to which process, which goes to another process, it's not entirely clear. And then we also have an even bigger, more complicated molecule like TOS, which unless you've sort of stumbled into a sort of Goodwill Hunting chemistry-esque film, you can't just walk up to somebody and say, hey, look at this molecule. What are the top 3 most important neutral dissociation processes that we need to look at? Nobody really has a clue. It's sort of, you can't just blink a couple times and blurt out the answer. So we need some sort of tool to start understanding what is it that's directing these neutral dissociation processes? How do we know which ones are going to be important? Which ones can we ignore? And this is where my research group for my PhD project came in. So my supervisor on the left, Charles Schilling, he sort of spoke with Quantemol. Quantemol brought this issue to their attention, and they said neutral dissociation is one of the big topics, right? And perhaps a little, as all professors are very sure in their abilities, he was like, no problem, we'll fix this. So he had the idea that if a neutral association for electron impact is so similar to photodissociation, he's been working on photodissociation ab initio molecular dynamics methods for decades. Surely all of these methods that are developed for a very similar process can essentially just be ported over with minimal effort to neutral association for electron impact. And so this ended up forming the basis of the second half of my PhD and the bulk of my thesis. But to sort of first see if these methods could be applied, our senior postdoc, Dima Makov, tried to essentially port over these methods as a proof of concept. And so what we did was we took this very same idea that we had before, this cartoon. We would take a molecule, optimize it in single state geometry, assume that it excites instantaneously into the lowest triplet state. We then give it a bunch of thermal kinetic momentum. So this is how we sort of sneak temperature in. And then we use DFT to propagate the molecule to see where it breaks, when it breaks, what pathways are important. And he did this to begin with a couple molecules that are a little bit smaller. So C3H2F6 and C3H2F4. So we have this molecule here. The first step that we did was to ask Quantemol which states are actually important, which states is it that we should be looking at. And they gave us back these cross sections. At the time, I was not part of Quantemol, so I was on the receiving end of the consultancy. They gave us back these cross sections, which show that around 12.5 to 13 eV, there appears these two triplet states that are, at least at the beginning, degenerate. So you can't really tell which one is sort of most important, which one is actually being excited to. So this is the first molecule. The second one has a much sort of more interesting picture, and that it has this double bond here, but also the lowest triplet state is separated by quite a wide margin. And so here you can sort of say at lower energies, definitely is this lowest triplet state that is being excited to. And so we had to ask the question, what happens on this other second triplet state here that sort of is degenerate? So we ran dynamics for this molecule, and we saw if you start it in the lowest triplet state, the population of the molecule of the excitation generally stays in the lowest triplet state. If you start in the highest, it just falls straight down back to the lowest. And so a nice little assumption to save quite a lot of computational time, quite a lot of computational power is saying, okay, this happens on a range of 50 femtoseconds. What if we say it's actually 0 femtoseconds and we just run everything on the lowest triplet state? And so they did this, and we had these sort of dissociation yields for the molecule without the double bond. And we see that the CHs break the most, CCs break the medium amount. Our internet connection is slightly unstable. That was found later on. And the CF bonds have the lowest dissociation rate. This is not particularly mind-blowing. CF bonds are very difficult to break. Nobody is sort of surprised by this. What is surprising is when we look at the molecule with a double bond and we look inside the different dissociation rates, we can see that closer to this double bond, the CF bond is actually dissociating more than the other three CF bonds at the other side. And so this sort of gave rise to the direction of the rest of the project, which is, what if these features like double bonds can localize the excitation to the triplet state? And what if these are the real important features in how to predict what bonds are going to break the most and the quickest? And so we came up with this electrophore model, which is very much the name sort of inspired / stolen by the chromophore in photochemistry, which is a functional group that localizes the excitation by a photon. And so the sort of idealized dream is, what if we fully understand what these electrophores are, which ones exist, and how they work? Could we predict, Goodwill Hunting style, what type of neutral association pathways are we going to get if we can just look at a picture of a molecule and say, oh, here's your electrophore, here's exactly what's going to happen. So the double bond was the first one we identified. And then even though I do have a chemistry PhD, perhaps it's not the most chemistry wise thing to say, but what if we assumed that an oxygen, which is in a lot of potential replaceable classes, can be seen as double bonded to itself via its lone pairs? Could this also localize the triplet state by having this high electron density? And so I began to look at some molecules that contained oxygen. These were sourced in a South Korean paper that were looked at as potential ingredient replacements for C4F8, which is a low global warming potential. And we can see when we plot the dissociation yields, the CHs are very high. That's because these simulations were done at 5,000 Kelvin, which is quite a high temperature even for high temperature plasma. And they're sitting around 30%-ish yield for CH bonds in both molecules, which means one of these CH3s is essentially dissociating in every trajectory. But we also see that the oxygen atom, which we presumed would be an electrophore, is very active in dissociation, and is always the highest, or perhaps you could argue joint highest with CC bonds. We can also see that the electrophore on the left, this molecule is sort of more symmetrical, and it has this electrophore in the center, closer to a lot more adjacent bonds, and actually has barely, but a higher overall dissociation yield than the other one, as the electrophore is capable of affecting more bonds. So the real differences between these molecules become interesting once you look at the individual bonds as opposed to bond types in general. And we can see that for the symmetrical electrophore isomer, we have this sort of almost symmetrical CC bond breakage. But when we have this N isomer over here that is more separated, the electrophore is very much on one side. You can very easily see which side this electrophore is on by looking at the dissociation yield of the closest carbon, which is almost double that of the other. If we then look at the CF bonds, which are the least associative out of all, this pattern is also clear. We have a very clear 15% dissociation yield for the symmetrical isomer, and then we have a more symmetric, but not quite symmetric enough, as one would like, on the I isomer. But when we look at the shifted electrophore on one side of the molecule, there's a very clear first, second, third place of can you get close to the electrophore or not. So the good news is we ran these simulations and we essentially came to the conclusion of if you know that a CF bond breaks less than a CC bond, and if you know how close the electrophore it is, you can essentially predict the order of bond breaking for every single bond in this molecule. So we then look back at the paper where we took these molecules from, and they have this very handy little mass spec at the end where they label the molecules from the mass spec, but also include these very little nice red highlighted lines where the authors conclude these are the bonds that are most involved in dissociation. Now, unfortunately, this is a mass spec of a whole plasma reactor, so I can't just say this is 100% neutral dissociation. It's a whole mixture of things, but it's at very least nice to have a little bit of validation that we do find that actually when we have the electrophore on one side of the molecule, it's only this CC bond that is very dissociative. When it's in the center, we have a mixture. We also looked at this molecule that was in a second paper by the same authors, where the electrophore is now an alcohol. And we can see that quite differently to the other molecules, the CO bond dissociation yield that was the highest before is now sitting next to the CFs instead of the CC bonds. That's because this OH peak is entirely dominant, and the scale is not the best, but I think it's something like 92-93% dissociation yield. So in 93% of trajectories, this hydrogen atom on the oxygen is just ejected. It's thrown off almost instantly. And this has a knock-on effect of because the oxygen has already gotten rid of an atom, it's not particularly interested in losing more. And so this CO bond then becomes very non-dissociative, which has knock-on effects throughout the whole molecule because the CC bond that is now next to the oxygen becomes even more dissociative than it did in the other two pair of molecules. And if we look at the CF bonds, we can see that they have a very low dissociation yield compared to the other ones. The highest here is around 4%, and the other molecules we're getting 8 to 16%. And this is because we have this CH2 right next to the oxygen, which I'm attempting to brand it as some sort of hydrogen buffer. If anybody has sort of brainstorming ideas for a catchier name, I'm open to talk to you afterwards. And this hydrogen essentially displaces the fluorines further away from the electrophore, which is controlling the neutral dissociation, and therefore significantly reduces the yields. And so what you can do is you can sort of shift around where these hydrogens go, and you can control your fluorine dissociation yields. If you want them to be high, you can swap them with the fluorines. If you want them to be lower, you can potentially add even more hydrogens and space out the fluorines even further away. And so the CF bonds have this lower dissociation yield, but they are still very much structured by, if you had a ruler and you look how far away is it from the electrophore, we have CF3 the closest, CF2 the second place, and last place we have CF3 at the complete other side of the molecule. And lastly, the molecule that I looked at from these sets of papers was this molecule here that has both a double bond and an oxygen. So it's two potential electrophores. The CC bond appears to be the most dominant electrophore by the fact that the dissociation yield is the highest. But now that we don't have this alcohol functional group, we sort of have regained the intense CO dissociations that we didn't have before, but did have in the two original molecules. If we investigate the CF dissociations that occur in this molecule, the one C4F atom that is wedged between the two potential electrophores actually accounts for over half of the dissociation yields of all 10 CF bonds that are in this molecule. So even though the CC bond does appear to be the actual electrophore here, the oxygen is still playing a part in helping this CF bond dissociate. So I went through these sort of 4 molecules. We ran them. All these results were at 5,000 Kelvin, but we tried to sort of step walk it down. I looked over all of these patterns that we found, and we came up with these electrophore trends. So in the paper I published, we called them rules, but I think it's probably better in hindsight to not claim that we've fully solved it yet, that we fully understand it, but we do have these insights. We do have these electrophore trends that double CC bonds and oxygen atoms can function as electrophores. They can localize the excitation. They can direct the neutral dissociation pathways of a molecule. The rapid dissociation of the CH and also the OH bond can therefore affect the rest of the dissociation pathways. Because if you know that you have an alcohol and your first bond broken is always going to be an alcohol, we can very much sort of look at the rest of the molecule and ask, okay, what happens to this radical that has now lost the H of the OH? The oxygen atom is an electrophore in a multiple of functional groups. It doesn't have to be an ether. It doesn't have to be an alcohol. It works in most. The double bond can actually have a larger dissociation yield than a single bond. Now, this is not one of the two of the double bonds breaking. This is a full rupture, a full cleavage of the molecules moving apart, which is surprising. And that there is a hierarchy of electrophores that do exist, and the double bond seems to outcompete the oxygen atom. I'm aware that due to time constraints and not wanting to have a million slides of graphs that may not be completely understandable, I haven't included all of the evidence I have for this hierarchy. But you'll either have to take me at my words, or I can set you up for a very easy question to ask me. It's up to you. And so this is sort of where we left off at the end of my PhD project before I joined Quantemol at the end of last year. Since I've joined Quantemol, there has been some sort of recent method developments that I've been working on. ECPs are now included in the molecular dynamics code, which allows us to look at larger molecules, which is sort of always the bane of theoreticians. You have a model, it works for a very small molecule, and then somebody's interested in it, and they say, what about this molecule that's 10 times the size? How would it work for this? So this is one step sort of closer to being able to run these large molecules, not only because there are more atoms, but also the heavier atoms, where if one of your molecules has a metal center, before untouchable, now semi-feasible to feasible. A lot of investigations are ongoing into the temperature dependence of these trends. So one of the first things that I always heard back when I said 5,000 Kelvin was, oh, actually, the highest we ever get is 1,000 Kelvin. What about at room temperature? How do these things work? So we're looking into simulations at lower temperatures, speeding up our simulations so we can reach these lower temperatures and still have it finished within my lifetime. And so soon we should be able to sort of have a clear idea not only of the insights into neutral dissociation, but also how you can sort of step up these trends as you go higher and higher in energy. So in general, how is this useful? It's useful to Quantemol in terms of once we have these insights into neutral dissociation pathways, we can then use it to inform better decision-making of how we form our neutral dissociation cross-sections. We can sort of generate our own approximate branching ratios that can then be used to weight the cross-sections I showed in the beginning. The branching ratios can also be used to populate QDB, which currently has some very limited ones, but we could definitely use this to improve QDB's data, which neutral dissociation is one of the big gaps at the minute. And so hopefully better insights into this process can help Quantemol as a whole, which would help us help you. Thank you for your attention.